For the integration technique, partial fraction decomposition, instead of recalling a differentiation rule, I want to actually go back to the process of finding a common denominator in order to combine rational expressions. So you'll see here I put up 2 over x plus 1 plus negative 3 over x plus 2. If I wanted to combine that into just one single expression, then we could get a common denominator by multiplying the two respective denominators and essentially then cross-multiplying them into the top. So this shows the process for which I would do that, and we can see that we could end up expressing that as 1 minus x divided by x squared plus 3x plus 2. So the process of partial fraction decomposition is actually the reverse of that. So if I started with something like we have on the right side here, we want to decompose that into pieces like we have on the left here. And in fact, partial fraction decomposition itself is not technically involving integration. We use that in order to simplify what we're trying to integrate. So we're going to use it in the reverse order. So imagine here we need to integrate what we have ended up with on the right side there. Now, we have the hindsight of being able to notice that I can break it up into the pieces that we have on the left. And what we'll see is that those pieces are things that I can much more easily anti-differentiate. But the question here is, how would I come up with those pieces, right? We have the ability to work backwards here. Well, that's where partial fraction decomposition comes in. Suppose you encounter this integral. First of all, the fact that the denominator can be factored into what we call distinct linear factors. So first of all, distinct, what I mean there is it's not x plus 1 times x plus 1, right? Those situations occur. What we're going to look at specifically here is not going to be eligible for that. Linear is that it's x plus 1 and x plus 2. If you had, say, x squared plus 1, that's not a linear factor, and you can't break that up into linear factors. We call that an irreducible quadratic. So I'll point out for the syllabus of this course, we are only considering distinct linear factors. If you were to study the technique of partial fraction decomposition, you'll see it's much more broad and it can account with things beyond that, but we're just not going to look at that. And the other thing that you'll note for our examples that's going to be important is the degree of the denominator that we have here has to be at least as large as the degree of the numerator, and I should say we want it to be larger. So we're going to need the denominator degree to be larger than the numerator degree. So these are all things that you'll note in our examples that we have that occurring, but just to kind of point out, that is our specific focus. So if I see these things, then I think partial fraction decomposition. And in that instance, my instinct is to take the integrand. So I'm going to ignore the integral symbol for a moment. And I'm going to write it in its factored form. And my goal is to be able to find constants a and b such that I could express this as a over one of the factors plus b over the other. And I happen to just put x plus 1 under a and x plus 2 under b. It doesn't matter. Okay. So essentially, the having distinct linear factors and having the degree of the denominator greater than the degree of the numerator is what allows us to know that it is possible to find constants a and b such that this is true. So with that guarantee, then we want to go about trying to find what those constants are. And I'm going to take this expression and multiply both sides by the common denominator here. So multiply both sides of the equation by that. On the left-hand side, if you multiply by its denominator, you're just going to get the numerator. Now, if you multiply what I've boxed in pink by this term, notice the x plus 1s will cancel. So you'll really only have a multiplied by x plus 2. Likewise, if you multiply what I have boxed in pink by this term, b over x plus 2, the x plus 2s will cancel, and you only have b multiplied by x plus 1. So this is much nicer in terms of allowing us to try to find the constants a and b. Now there are lots of ways you might go about trying to find these. What I'll point out is, importantly, the equation we've established here needs to hold true for all values of x. So we can plug in any values of x we'd like, and we know that the two sides have to be equal. A nice simple way to go about finding those coefficients is to specifically choose the roots of the denominator. So in this case, -1 and -2. So look for the values that you could plug into the original denominator that would have made it 0. And the reason we can do that is, you'll see what happens is nice here. These are the values that make a and or b, a or b vanish when I plug them in. So if I plug in x equals -1 to the equation that I have underlined in blue here, well, on the left-hand side, I'm going to get 1 minus a -1, so that's 2. And on the right-hand side, I'm going to get a times -1 plus 2, which is just 1, plus b times 0. And the times 0 is what's nice, because notice that I go from 2 unknowns to this equation. It's just telling me 1 unknown, and I can figure out what a is. So 2 equals a times 1. From this, I know that a is 2. If I plug in -2 to the equation underlined in blue, on the left-hand side, I'm going to get 1 minus a -2, so we'll get 3. And I get a times 0, so we get to ignore that part, plus b times -2 plus 1, which is -1. 3 equals -b, so we get that b is equal to -3. So what does that tell us? Well, in this case, that means that I can replace a with 2. I can replace b with -3. And notice that's exactly what we started with up here. So what we've kind of outlined is the way that we would be able to find those pieces that we want to break this up into. So what does this tell me? This means then that the integral that I'm trying to find is equal to the integral of a, which we said was 2, over x plus 1, plus b, which we said was -3, divided by x plus 2. So we've replaced the original integrand with its equivalent representation. And the reason this is advantageous is, notice what we have here. We have, I can split this up as just the integral of 2 over x plus 1. And maybe let me put the minus the integral of 3 over x plus 2. And I can deal with these integrals. Because these are linear factors, I can say that these are going to be multiples of natural log. So we get 2 natural log x plus 1 minus 3 natural log x plus 2. And of course, we would also get an integration constant because this is an indefinite integral. If you have a definite integral, there's really no problem here. Any bounds that you would have on the original integral would apply to both of these integrals you break up here. So that's the main thing to consider. The other thing to think about is, because we're always breaking up into linear factors, you will get a natural log. We do have to be careful if you ever have one where you have a coefficient in front of x, then you have to be careful about the antiderivative, just as a reminder. We'll see some examples of that. But for instance, if you had 1 over 2x plus 5, you would get the natural log because that's linear. But because of that 2, you'd have to bring out a 1/2. So that's what I mean there. Here, the coefficient was 1. We didn't have to worry about that. You can think of that as u substitution, but you can also just think that what we have to account for is that the chain rule would have brought out a factor of 2. And then the last thing I'll mention is that because of log rules, there are lots of ways that you could express this final answer. How we wrote it here is fine. I'll point out sometimes when we talk about improper integrals later, it might be better to condense things. So this is equal as well to the natural log of x plus 1 squared minus the natural log of x plus 2 cubed, because of log properties where you can bring in the multiplier outside. And then further, you could write this as a single log by saying that the difference of two logs you can write as the log of a quotient. So this is also a suitable way to express the final answer. And we will address later that sometimes with definite integrals, especially when we're looking at improper integrals, being able to express it as a single log function can be helpful.